Dear third prep, today we will introduce a new lesson, which is relation between tangents. We have taken before that if I want to draw a tangent from endpoints of diameter, two tangents from two endpoints of diameter, they are parallel to each other. So if AB is diameter, therefore straight line L and straight line K are parallel to each other. Second, if I have two tangents drawn from one point outside the circle, if I draw a tangent like L and K from point C outside the tangent, the two tangents here are intersecting. I can call CA and CB two tangent segments. We know that the straight line L or the straight line K is a tangent. The tangent is a straight line. But if I want the starting and ending point like AC or BC, this part of the tangent called tangent segment. We have theorem here, the two tangent segments drawn to a circle from one point outside it are equal in length. So the two tangent segments here, AC and BC, are equal in length. So we say that since in AB and AC are two tangent segments, therefore they are equal. Corollaries. Corollary number one, the line joining the point which is outside the circle and the center, or the point of intersection of the two tangents and the center, this line consider an axis of symmetry of the line BC, which is called tangent chord of tangency. So the straight line passing through the center of the circle and the point of intersection of two tangents is axis of symmetry of the chord of tangency. If so therefore AM will be perpendicular to BC and BD equals CD. Axis of symmetry is the perpendicular bisector of the line segment. Number two, also the line joining the center and the point of intersection of the two tangents bisects the angle between the two tangents here and the angle on the central angle between the two radii BM and CM. So this line here bisects the angle A and the angle M, they will be equal in measure. So AM bisects angle BAC, number one, angle 1 equal angle 2, and bisect the central angle BMC, so angle 3 equal angle 4. And we know, of course, that MB perpendicular to the tangent AB and the MBC perpendicular to the tangent AC, as we have taken before. For example, I have two circles here, and from point A outside the circle I draw two tangents AD and AE for the greater circle and two tangents AB and AC for the small one, and he wants the value of X and Y. First we will draw circle by circle. In circle N, the small one, AB and AC are two tangent segments, so they are equal in length. So AB equal to AC, so X plus 2 here is equal to 6, so therefore X equals 4. In circle M, AD and AE are two tangent segments, so AD and AE are equal. Y minus 3 plus 6, all this segment from A to E, Y minus 3 plus 6 is equal to X plus 2 plus 4, which is 6 plus 4, because X here is 4. So Y minus 3 here equal 4, adding 3 to the other side, Y equals 10. Another example. Here in the opposite figure, AB and AC touch the circle at B, means AB and AC are two tangent segments or tangents. And I have AB is parallel to EC, measure of angle A 50, E wants measure of angle B DE, or measure of angle D. First, if I have AB and AC are two tangent segments, therefore they are equal in length. So the triangle ABC here is an isosceles triangle. Therefore measure of angle ABC equal to measure of angle ACB equals 65 degrees. So each one of them here is equal to 65. Since AB parallel to EC, I have here alternate angles, ABCE. I have letter Z here. So measure of angle ABC and the measure of angle DCE are equal in measure because they are alternate angles. And because E, D, B, and C, 4 vertices of quadrilateral lie on the same circle, I can say that the figure DBCE is a cyclic quad. And we know that in the cyclic quad, opposite angles are supplementary. So if a measure of angle C here is 65, I can easily find measure of angle D by subtracting from 180 equal 115 degrees. The converse of this theorem. Number 1, the definition of the inscribed angle. We have taken before that the circumcircle is the circle passing through the vertices of triangle. Now I have a new definition of a new circle, which is an inscribed circle, which touches the 3 sides internally of a triangle, of a quadrilateral, of anything. So this is called the circle, inscribed angle, inscribed circle to triangle. Here this is inscribed circle to quadrilateral. So the center of the inscribed circle here is the point of intersection of the bisectors of the angles. This information, this node, you have to know it well. The center of the inscribed circle to triangle is the intersection point of the bisector of angles. If I bisected angle C and B and A, the 3 bisectors will intersect at M, which is the center of the circle. We want to know the number of common tangents. We have taken the position of the circle before, the 2 distant circles, 2 circles touching internally, intersecting or touching externally. Here, in the 2 distant circles, I have 4 common tangents. Common tangents mean the same line, line 1 or 2 or 3 or 4, is a tangent to the 2 circles at the same time. So I have here 2 external tangents and 2 internal tangents. The outsider tangent, line 1 and line 2, called the external tangents. The 2 tangents inside called internal. And generally, in the 2 distant circles, we have 4 common tangents. In the touching externally circles, I have 2 external, 1 internal, which is line 3. So I have 3 common tangents. In intersecting circles, I have 2 common tangents, and both of them are externally. There is no internal tangent. And the 4 touching internally circles, I have only 1 common tangent, and it's external tangent. And the other 2 positions, there is no common tangent for them, which is one inside the other and concentric.